In this video segment, I want to look at the concept of inverse interpolation. We know that in interpolation problems, we are given a query value for x and we are asked to find out the value of the function at that query point. In inverse interpolation, as the name suggests, we are trying to do the opposite. We are given the value of the function as f of x is equal to d and d is specified. Now we need to find out the value of x that makes this true. So the problem is find a value of x such that f of x is equal to d. The starting point is still the same. We have tabulated data, and based on the tabulated data, this question is being asked. So you can imagine a strategy like this. First of all, we go ahead and construct the polynomial using tabular data. For example, one could use the forward differences by constructing the Newton's forward difference table and get a polynomial of this order. This is something we have seen before. So we can construct a polynomial of order m minus 1. That means the highest order of alpha in this polynomial will be m minus 1. So again, we are assuming we have m data points. And therefore, all the ideas that we looked at when we constructed the interpolating polynomial using Newton's forward difference table hold true. Now, we are interested in finding f of x is equal to d. And we know we can represent x as the reference point plus alpha times h. Once we recognize that, I can turn this problem f of x is equal to d as one where we are trying to find out the alpha value that will make this true, because the step size is fixed given tabular data, and we can assume that h is constant in this data set. That means the data is equally spaced. We know the reference value x1. So we are trying to find out this value of alpha that will make f of x1 plus alpha h equal to d. Once we find alpha, we can find the value of x as x1 plus alpha h. So here what we have done is, so with that idea, we will set this polynomial in alpha equal to d. And then we would determine alpha. Once we find out alpha, we can find out x. Now, how do you find out alpha? You can find out alpha using many of the techniques that we have learned so far. You can find out alpha using the roots command in MATLAB. You can also set up an iterative scheme of this particular form, where you have alpha on the left hand side and the right hand side is a function of alpha. And then we can set up the iteration scheme by starting with some guess for alpha, putting it on the right hand side, evaluating this function and getting this new value of alpha. So this is something like alpha new is equal to a function of alpha old. So we start with a guess value, which we can call as alpha old, find out the value of g of alpha old and call that alpha new. If alpha new is very close to alpha old within a convergence tolerance of, let's say, 10 to the power of minus 12, then we will say the iterations have converged and we will report the value of alpha. If not, we can take this newly computed value of alpha, you can assign it as x old and put it back here. So you can set up this iterative scheme. This kind of scheme is called fixed point iteration scheme. Let's get into the equations. The polynomial at x is going to have a value d. In fact, we are saying this should be equal to d because this approximates the function and we want the function to have a value d. Therefore, instead of the function that we do not know fully about, we are going to work with the approximation of that function, which is this polynomial. So the left hand side is set to be D because that is what is given. So the left hand side is D and the right hand side is going to be 1 times f of x1. So that is going to be f1 plus alpha delta f of x1 will be alpha delta f1. That's what you see here. And so on until the m minus 1th power polynomial on the right hand side. So do not think that this is an infinite series. It will stop with that particular term that contains alpha to the power of m minus 1. Now, what I'm going to do is, I'm going to take this alpha delta f1 to the left hand side and move this d to the right hand side. So this goes here and that comes here. So the left hand side now will be alpha delta f1. And I'm making sure I take care of the sign changes, etc. Because when alpha delta f1 comes to the left hand side, it will be minus alpha delta f1. So to have the left hand side as alpha delta f1, what I do is I multiply the equation throughout by minus 1. So I'm sure you can see how this equation becomes this. Kindly note this plus sign has changed to minus sign. This plus sign has changed to minus sign. f1 minus d will become d minus f1. So everything is intact. Now I can divide throughout by delta f1 and get the left hand side to be just alpha. So alpha is equal to 1 by delta f1 multiplied by this whole thing. So that is what is shown here. Now we see the left hand side is alpha. The right hand side is a function of alpha. And everything else in the right hand side is known. D is known. It's specified in the problem. We know what is the value of F1. That's from the data. From the Newton forward difference table, we can find out these forward differences. And therefore, on the right hand side, everything is known except for alpha. So this left hand side, alpha, we can just label it as alpha nu. And the alphas that occur on the right hand side, wherever it occurs, all these alphas will be referred to as alpha old. So this whole thing is a function of alpha old. So we can write this as alpha new is equal to g times alpha old and set up the iterative scheme starting with one value of the initial guess. You can use other ways of estimating alpha as well. This is only one choice. Instead of saying alpha new and alpha old, we can get a little more mathematical and just say alpha at the I plus 1th iterate is alpha new and alpha at the previous iterate, which is the ith iteration, that is alpha I. So we can set it up in this form. Alpha I plus 1 is equal to g of alpha I. So I can start with an initial guess alpha 0. And then I can calculate g of alpha 0. That means I put the alpha 0 on the right hand side here and evaluate this whole thing. So I'm going to get that to be g of alpha naught. That will be assigned to alpha 1, which is this. So alpha naught I is 0, you will get alpha 1. Now I will look whether alpha 1 is very close to alpha naught or is it different. If it is different by more than 10 to the power of minus 8 or 10 to the power of minus 12 in magnitude, I will take this alpha 1 and put it here as alpha naught. I'll get a new alpha 1. Or I will use now alpha 1, find out g of alpha 1, that means evaluate the right hand side and get this g of alpha 1, and I will find out alpha 2. Now I'll see whether alpha 1 and alpha 2 are near. If yes, report the answer. If no, I'll get alpha 3 using g of alpha 2. So I'll take alpha 2 value and put it on the right hand side to get g of alpha 2, which I'll look at as alpha 3 and so on. So what is a good value to guess for alpha? When we start, what is a good value to take for alpha? Because that is often the question, right? In the iterative scheme, once you set up the iterations, the question that is asked is, what should be my initial guess? So what could be a good guess for alpha. What I might do is I might simplify the problem by just taking this term, ignoring all of this because we are just looking at an initial guess. So we'll ignore all those things and say alpha naught, my initial guess, is going to be d minus f1 by delta f1. So d is given in the problem statement. So this is given. F1 is known from the tabulated data. Delta F1 can be easily computed as F2 minus F1. And therefore, this can serve as a good starting guess for alpha. Once we have alpha naught, then we can get to alpha 1, alpha 2, alpha 3, etc., etc. So now this data is given to us. The tabulated data is given to us, and the value of d is specified to be 100. So we are to find the value of x that will make this true. So for this data table, we use the Newton forward difference table to come up with three different interpolating polynomials of different order. Just to recall your memory, these were the three polynomials that we constructed using x1 is equal to 2 as the reference point. Now let's take this third polynomial that's listed there. That means we are looking at P3. So P3 at 2 plus alpha is given to be 8 plus 19 alpha plus 18 times alpha into alpha minus 1 by 2 factorial plus alpha into alpha minus 1 into alpha minus 2 by 3 factorial times 6. We will ignore this residual term. So in our problem, this is given to be 100. So 100 is equal to 8 plus 19 alpha plus 9 alpha times alpha minus 1 because 18 divided by 2 factorial and 2 factorial is 2. So 18 by 2 is 9 plus 3 factorial is 6. That would cancel with the 6 to have alpha into alpha minus 1, alpha minus 2 as the equation. So now we can solve this using roots command in MATLAB to find out alpha. Another way is to do what was previously suggested. So I can bring this 19 alpha to the left hand side. So it will be minus 19 alpha is equal to 8. This 100 comes to the right hand side. So it will be 8 minus 100 plus 9 alpha into alpha minus 1 plus alpha into alpha minus 1 times alpha minus 2. And then we divide throughout by minus 19 to get alpha is equal to 1 by 19 minus 8 plus 100, that will be 92, minus 9 alpha into alpha minus 1 minus alpha into alpha minus 1 into alpha minus 2. So this is how you set up the iteration scheme. The trick is the alpha on the left, we will just call it as alpha new, or we can call it as alpha I plus 1. The right hand side, wherever alpha occurs, we can call it alpha old, or we can call it alpha I. The same for this alpha, for this, and for that. All of the alphas on the right hand side are either called alpha I or alpha old. And this is the same as alpha I plus 1 is equal to g, some function of alpha I. You can see that, right? This is some function of alpha I. And the left hand side is alpha I plus 1. What is alpha 0? An initial guess. An initial guess can be this 92 by 19. What is 92? It is d minus f1. f1 is 8, as you can see, and d is 100 in our problem. So d minus f1 divided by delta f1. Delta f1 is 19. If you remember, that's how we got the 19 into these things, into these polynomials. So alpha naught is nothing but d minus f1 divided by delta f1. And using the numbers that we have, we showed in this particular example, it will come out to be 92 by 19. So that is a reasonably good initial guess. We can set up an iterative scheme using a few lines of code. Things that we wrote for the Newton method will work just fine. In fact, this problem can be solved for alpha using the Newton method. So there are many ways of solving for alpha. Once I get the value of alpha, then x will be equal to x1 plus alpha h. So x1 is 2 in this case, and h is equal to 1. And once you get the value of alpha from solving this equation in any way, using the roots command or using Newton method or using bisection method or using this fixed point iteration idea, whatever method you get, once you get alpha, you just put it in there, and then you can find out the value of x. And that is the answer to the problem. So this is how inverse interpolation problems can be solved. Thank you for your time.